Hey guys, I hope you're doing well. Uh, Looking forward to seeing you guys again tomorrow on Wednesday. So I wanted to. It's actually Saturday right now, and I'm putting together a little video here to just show you kind of the protocol for or some tips on solving these specific heat problems. So I'm just going to make this short and sweet. We can talk a little bit more about the theory and kind of what it all means maybe tomorrow. So let's just take this problem, and this is different from the problems that this is not one of the problems that's on your worksheet that you'll be tackling this period, but it's very similar. So hopefully as we go through this problem, this will kind of help you know how to approach the ones that are on the worksheet. All right, so the problem reads, you've got 25 grams of iron, and if that 25 grams of iron absorbs 500 joules of heat, and the starting temperature of the metal is 21 degrees Celsius, what's the final temperature of the iron going to be? Okay, and then I give you here in parentheses the specific heat for iron. Okay, and these units, I know they look rather bizarre. It's joules per gram per degree Celsius. And so the way to think about this is if you had 1 gram of iron and you wanted to raise the temperature of that 1 gram of iron by 1 degree Celsius, it would require putting in 0.45 joules of energy. Okay, so it's just almost half of a joule. So again, if you have 1 gram of iron and it absorbs about half of a joule of energy, the temperature of that iron will go up 1 degree Celsius. Now, from your reading, you've probably seen that water, the specific heat of water is a lot higher than that. It's 4.18 joules per gram per degree Celsius. So what that means is if you have 1 gram of water and you want to raise its temperature by 1 degree Celsius, you're going to have to pump in a little over 4 joules of energy. Okay, so that's well over 8 times. It's about 9 times as much energy is required to heat water. You know, 1 degree Celsius. So water can, it can store more heat energy without raising its temperature. So that's just, kind of a little tidbit here, a little extra. All right, so let's get down to business. Now, on pages 476 and 477 of your textbook, it talks about specific heat, and it gives you this equation which relates the amount of heat energy that can be absorbed by, an object, and it's related to that object's mass times the specific heat of that object times the change in temperature of that object. Okay, and one thing that the book does not mention, I don't believe, is the change in temperature. There's a very specific way to calculate that. Delta T is defined as T final minus T initial. All right, so the point that I want to make clear is that this delta T is not an absolute difference. Okay, it's not always positive, in other words. So I think you can see that if the temperature of an object goes down, okay, then the final temperature will be less than the initial temperature. And then you will get a negative delta T. Okay, so that it is possible to get negative delta T's. All right, so let's take a look at this. So we've got 25 grams of iron. All right, so we know the mass. We know how much heat is going to get absorbed, so we know that variable. And let's see here. Do we know the specific heat? Yes, we do. It was given to us in the problem. And the question is, what's the final temperature of the iron? All right, So at your first impulse, the first thing that you might be thinking is, well, wait a minute. My formula doesn't have final temperature. I don't have a variable for final temperature in this equation. Well, that's true, but you do you do have this term for delta t, and I've just explained how delta t relates to final temperature and initial temperature. And you do have the initial temperature. That information is given to you. All right. So this is this is where you got to kind of think outside the box a little bit. So what we'll do is we will first let's just solve for delta t. All right. So that's going to be our variable because we know q, we know m, we know c. Let's solve for delta t, and then when we get that, we can stick that value into this expression, and then we can easily solve for t final, right? Okay, so if you do the algebra, and I know you guys sometimes get freaked out at how I do algebra, but you've got to trust me. When you solve for delta t, you're going to get q over m times c, all right? And now we can, let me clean things up a little bit here. Now that we've isolated for the variable that we're interested in, now we can plug in the values from the problem. Okay, Q is 500 joules, so 500 joules. All right, M, that's mass, that's 25 grams. Okay, I'll use parentheses to indicate my multiplication. And then specific heat is C, and so that's 0.45 joules per gram degree Celsius. Okay, so that's what we've got. Now, if we do a little unit analysis, let's see what happens. So looking in the denominator, I can see that grams cancels with grams, and now then this joule is going to cancel with this joule, and so what we have in terms of units is we sort of have 1 over degree Celsius. Isn't that weird? Because this degree Celsius is in the denominator of the denominator, so to speak. So then this will flip up to become just degrees Celsius, and that's exactly what we want. Okay, so that's fine. So delta t, then we are ready. I'll put the unit here so that we're ready. Now we take the calculator and we take 500, divide by 25, and then divide by 0.45. And when you do that, you should come up with 44. If we round to the nearest whole number, we get 44 degrees Celsius. All right, let me erase this part. In fact, I did this earlier. If I can find my calculator, let me just double check here. 500 divided by 25 equals 20. And then when I divide by 0.45, yep, 44.4, which I'm going to round to 44 degrees. All right, so that's delta t. But the problem is asking for the final temperature, right? We don't care. They don't care what delta t is. They want to know what the final temperature is. All right, so this is when we go and use this expression, okay? And I think, you don't even have to go through the algebra for this, right? I mean, if the temperature has changed by 44 degrees, and we know the initial temperature was 21, then we're going to be 44 degrees warmer than 21. And we know it's going to warm up. It's not going to cool down. The iron is going to warm up because we added heat. So 44 plus 21 is 65 by my math. Okay, so T final equals 21 degrees plus 44 degrees Celsius equals 65 degrees Celsius. Okay, so that's I hope this helps a little bit. These are some of the things that you need to do to solve these problems. You start with this expression, the one that's given in your book, and I hope it helps to know that delta t is t final minus t initial. Okay, so best of luck on the problems on the worksheet, and we'll see you tomorrow. Okay.